Alright, this hopefully short video is about Hooke's Law, which is what we learned about today in class. So what we're going to talk about is when Hooke's Law applies and when it doesn't apply, because it doesn't apply for all springs. So, and then we'll talk about a quick application or examples of problems in which you would use these. So this should be similar to some of the problems that you, or the springs that you all did today for your lab. All of them appear to be quite linear. So this is some data that I just had from last year. And here is the data for a single spring of displacement versus force. So remember, our x-axis was displacement, and our y-axis was force, which is the okay. So they all appear to be quite linear. So the first thing that tells us is, one, the springs that we were using were linear themselves when they were single. The second thing that it tells us is even if we had multiple springs either operating parallel, which is two springs next to each other that undergo the same displacement, or whether they were in series, which is one spring on top of another one, so they're working together as well, they still have the same amount of stretch per string. It's just now, or spring, excuse me, but they're both vertical. Okay, so remember, series was like this, and then two springs like that, and parallel would be two springs next to each other and attached in some sort of way. Okay, but each time they still had that linear change. So if the single spring was linear, if you take that exact same spring and put it in series or in parallel, it will still be linear. But we'll talk about this tomorrow in class. What you need to notice is the slopes and how they relate to one another, how they relate back to that single spring value. For this particular example, the original slope, 1.097 newtons per meter, and so we're going to take that into account. For the single spring, when it was in parallel, it became 2.5, and it was in series, it was 0.545. So we'll discuss that more tomorrow, but the first thing we need to notice is that they're all linear. Now, the second thing you should notice is none of them have a y-intercept of 0, but it's pretty close to 0. Especially look at this one here when they're in series. Very, very, very close to 0 for the y-intercept. Okay? So if we were to actually write out the equation for each one, this would be force. Force equals y equals mx plus b, basically. Then the slope here, that's going to change for each one, and then it'll be the change in x, and then plus this y-intercept, but basically just f naught. And so the y-intercept should represent when the displacement is 0, what force is being pulled on the spring. And that should have something to do with gravity. Okay, so what we talk about is in this spring force, we had an applied force there. We added a weight, and that was pulling the spring down. So here is an applied force. And what happens is the spring force, here's us pulling the applied force in the opposite direction. Okay? We pulled the spring. So we added an applied force. The spring pulls back by the same amount. These should be congruent. But first thing you need to notice is that the spring always pulls in the opposite direction of the applied force. And so a lot of times you'll see a negative dealing with the equation. But if it is truly linear, then we look at the slope. And if we look at the units for the slope, it should be in newtons per meter. Because if we're doing y equals mx plus b, the y is our force, and our x is in meters. Just call it change in x. Don't write it right. Want to write it right. And this is your initial force here. Okay, so slope should be in change in y over change in x, so newtons per meter. And so let's think about what that means. What does this spring constant truly mean? And we usually call it K, but it could be called anything. And this means, let's make the easiest case of 1 meter. For every 1 meter, that means it would take 1 newton to stretch it if our slope was just m here. There's just 1. In this case, this one says for every 1 meter, it's going to take 3.5 newtons to get it to stretch that 1 meter. Okay? So this is a special kind of spring. This is a special kind of spring called a Hookean spring. And so this is Hooke's law. If indeed you stretch a stretchable elastic object, and that's what we call it, that's the technical term, would be an elastic object that contains a restoring force, something that's pulling back. And it always comes up to be linear for that particular object, and it follows what we call Hooke's law, named after Robert Hooke, very famous physicist. And Hooke said that that restoring force, that force that's pulling against the applied force of the spring, would always be equal to the spring constant K times the displacement. In this case, we're just saying the change in S, or you can say change in X. On the AP exam, it's actually going to say the force of a spring is equal to negative K times X, and X means displacement here. Okay, but this would be for a Hookean spring, and so and then that's the force that pulls it back. So if you add an applied force, it should be the exact same force pulling against the spring. And so when does that apply? Well, that only applies if it's truly an ideal spring. Ideal also means Hookean. So these two words are interchangeable. The springs we dealt with today are very close to being Hookean springs, but it has to meet a couple criteria. First is that the applied force is proportional to displacement. Okay, and for us, the ones we use today, that means that they just need to be linear, and they were. They were perfectly linear. They were very similar to this. We got a couple of cases of correlation coefficient of 1. I mean, that's amazing. Each cross section of the spring must be ideal as well. And so that means, you know, you can't have part of a spring that might be parabolic if you were to graph the displacement versus force, or vice versa. And the third, and this is the condition that our springs do not meet. When hung vertically, the spring is massless. And that sounds ridiculous. And that's why it's called ideal, and nothing in the real world is truly ideal, right? But if you're hanging the spring vertically, every coil from the bottom coil on up, so here's our spring. Okay, if you're hanging this vertically, this spring up here has some additional forces pulling on it. It has the weight of all the other coils. And that's why you tend to see them stretched out a little, and then they get more coils, more compact as you go on, because this top coil is supporting all of the other ones, and that's what makes it not truly ideal, and that's what's going to give it that non-zero y-intercept. So this is an ideal spring right here. Okay, at 0 there is 0 force, 0 displacement, there's 0 force. But if we know that it changes proportionally, then for a lot of the times we will assume a 0 y-intercept, even though we know in the real world that's not true. But we can just say for everything past this. Okay. Now, another purpose for that y-intercept is sometimes, especially for very tough springs, it takes it a little while to get past that first stretch. And that wasn't really the case with ours. We had some pretty easy to stretch springs here, but notice this y-intercept is 0.01432 newtons. Okay, so maybe it took 0.01 newtons before this one would even start to stretch. Okay, it's just how that it is, and the springs we use today were very easy to stretch. Now, again, if you always remember the units for K, it's going to be in newtons per meter, because we're graphing force versus the change in X, which was in newtons and in meters. Okay. And so it's just close. So just to reiterate, if this was our applied force, so this would be for the third graph, I'm pushing on the spring, I am applying this, then the spring force pushes back in the opposite direction. Okay, but by equal amounts, always. And if it is linear, then we can use Hooke's law. It's a Hookean spring. Alright, so just to check for understanding, which spring is going to be the most difficult to stretch? So these are all Hookean springs, so it doesn't matter in this case. But we can tell they're Hookean. They're all linear functions. They all have a y-intercept here at 0. Again, none of that really matters here. So think, pull on this spring. Well, which one's going to be the hardest? Which one will I have to apply the most force to get it to move the same distance? So these will depend upon the spring constant, K. And remember that's in newtons per meter. So let's think about that. All right, so let's say I want to stretch it 1 meter. Okay, and that would stretch by, I would need K newtons for it to stretch by 1 meter. Well, this is just slope, so whichever one has the greatest slope is going to take the greatest amount of newtons to stretch it 1 meter. So if you answered A, give yourselves a pat on the back. Because you're right, yay! Okay, so this will take the greatest force to stretch the same amount, the same distance. We always use 1 meter, or 1 meter. Let's look at another one. So here are 4 springs. They could be stretched, they could be compressed. In which case does the force exerted by the spring onto whatever object is being applied? So there's an applied force. I don't know if it's pulling on the string or pushing on the spring. I don't know. In which case is the spring force going to be largest? And the answer is E. Okay, so it's proportional to displacement. Force is proportional to displacement. And unfortunately, we don't know for any of these cases, that is a horrible line, but you get the idea. We don't know where the original position is. If we knew where the original position was, we could say, and if they all had the same spring constant, that would be great. But we don't know where it is. If they all had the same spring constant, and this was the initial position, then it would be D, if this is where I pushed it. Okay. Now let's say I move that here. And now this is my initial position. They all have the same spring constant, then it would be A. But without any of that information, without knowing if they have the same spring constant, which it does say a Hookean spring here, but without knowing where the initial position is, it's you cannot tell which one is the greatest force. Okay, let's do some more. If you're comfortable, you can stop the video now. But let's do 2 quick problems. A 20 centimeter long Hookean spring is attached to the wall. When pulled horizontally with a force of 100 newtons, the spring stretches to a length of 22 centimeters. What is the value of the spring constant? So the first thing that we need to notice is it's Hookean. So if it's Hookean, it should follow linearly. So the force of the spring will be negative K times X. Now, you actually don't have to worry about the negative. That negative simply means it's being pushed opposite the applied force. So the spring will always push against the applied in the opposite direction. So you can completely ignore the negative and not care about it. Okay, it's a directional thing. But what we're saying is, here's our spring. It's attached to a wall, so this is so we can ignore gravity. Okay, it originally starts out with 0.20 meters. That's our original spot. Okay, but then we pull with 100 Newton force, and now our spring gains an additional 2 centimeters. So our new spring length is 0.22 meters. But remember, X here is displacement. We're trying to find the spring constant. So if this truly is ideal, then the y-intercept right here would be 0. So this, our spring constant, if we look at our force, we have 100 newtons pulling it, and the spring constant should be pulling back in the exact same amount by 100 newtons. Okay, so this applied force should always be equal to your spring force. So we have 100 newtons is equal to negative K times the displacement. I'm going to ignore the K here because it doesn't matter. The displacement, careful here, is not 22. It's 0.02. So it's from where you started. Okay. And so dividing these, and we'll get our units here as well, 100 divided by 0.02 should be a really, really, really strong spring constant, 5,000 newtons per meter. So in order to move this thing 1 meter, we'd have to apply 5,000 newtons of force, which, I mean, if we look at this, we only moved it 2 centimeters and we applied 100 newtons of force. That's ridiculous. If we look at the next question, the same spring is now used for a tug of war. Two people pull on the ends, and they each apply 100 newtons. Okay, and we're going to assume we haven't reached the elastic limit, and it's going to overstretch. How long is the spring while it's being pulled? Okay, so you should notice on the last one, the displacement was 0.02 meters, and it took 100 newtons. I don't know why I do that. Okay, so this is your change in x, and this is your force. Remember, this should be linear. It's a Hookean spring. So if we're going to apply 200 newtons, it's just being pulled in two opposite directions, okay? But again, it's still applying 200 newtons, just one on each opposite end. It should just simply double, and it should be very simple. Okay, it's going to be linear. If I apply 300 newtons, then it's going to move 0.06 meters, so 6 centimeters. Okay, and that's it. But the biggest thing I can reiterate with this, especially for an AP Physics C course, is that we need to make sure that we only are going to use Hooke's law if it's an ideal spring. Almost every case it will be. It will either say an ideal spring or a Hookean spring. But there are a couple situations where it won't. And in those cases, we won't find spring constants because it could be of something like AS squared plus DS plus C. It could be a quadratic where S is the displacement. And in those cases, we'll be given some other way of finding it, maybe using work or something. And that's it.